Log on, tune in, find out. Another good idea from Cambridge.
This is Sergei Leonov, and Sergei will talk about design of population, PK, PD studies, approximation of the individual Fisher information matrix. Please.
Thank you for the introduction.
You have this
microphone?
Oh, I need for recording.
Yes, exactly. Oh.
Hello? Hello? Is it different? No? No?
You keep speaking using your voice.
But the point
Hello? Hello? Hello?
it's okay, but the thing is that it's for recording.
For recording, so it
Also Russ. It's also okay.
okay. All right. So I would like to start with thanking the organizers. I was sort of local organizer of the workshop, but you know the whole program is going on right now at the Isaac Newton Institute, and from the people here, I believe Basha and Rosemary were and more, and but I guess two of you took most of the responsibility. So thank you very much for organizing this event. As Basha explained in the introduction, we decided to have this POD or PODI meeting as part of the conference this week. And I believe already, so the POD day is today, so you haven't heard anything. But I think those members of POD community who listen to talks in other areas of optimal design have already benefited being exposed to new ideas and new problems. And I hope those of you who have not participated in POD before will learn hopefully something interesting today. At least you will see what people in POD community were doing for the past 5 years. So the talk, you see the title, it's about design of population studies for pharmacokinetics and pharmacodynamics primarily, and I'll pay some attention to different types of approximation of the Fisher information matrix. Let me start with the outline. Yeah, just want to mention that when I got this badge, there was a very strange affiliation on my badge, which I decided simply to cross out. And which is better than what it was. And many of you know we had a group in GlaxoSmithKline for many years, and I will be moving to Vertex in early September. The outline. I'll talk a little bit about POD workshops, what these workshops are about, and really try to give some introduction about different population software tools. We will have a discussion later today, and Franz Montre will provide much more details, but I would like to say a few things about what kind of problems we try to address in our tools, and say a few words about the comparison of different tools. But I think and everybody in our developers community think that it's very important to match the results. It's very difficult to find some benchmark tests to compare the results because the models are quite complicated, and it's nice when results of different software tools match, and that's happily what's happening. All right, Basha has already told you what PODs stand for. It's a short, small conference about theory of optimal experimental design for nonlinear mixed effect models and applications primarily in drug development, primarily in pharmacology, pharmacokinetics, and pharmacodynamics. We started the discussion of population software tools 5 years ago, actually in 2007. And this discussion and comparison goes on for 4 years now, and you will hear more today.
And what about future?
About future, we will talk in the afternoon.
After 5 years?
We'll talk about in the afternoon. And again, if you have questions, please interrupt me. So, all right, there are 5 tools currently available, and they are listed in alphabetical order. PFIM is developed in Paris, in France, and France Montré and her collaborators over the years are behind this tool. PK Stamp is our tool which we developed in GlaxoSmithKline over the last probably 7 or 8 years. PopDes is from Manchester. Kay Ogunbenro is here. He is one of the main developers of PopDes. PopEd is from Uppsala, and we have Joachim. Where is Joachim? And Sebastian, who also contributes to the development. And again, final in the list because of the alphabetical order only is Steve Duffel's tool, WinPopped, from New Zealand. So the tools they target optimum design for pharmacokinetic and pharmacodynamics models, but you can use these tools for other areas as well. For example, in GSK, some guys from chemical development approached us and were interested to use the tool because the background for the tool is mostly compartmental models, and those compartmental models are used not only in PK, but they obviously are used in chemical development too. So, few words about the comparison. As you all know, the key for optimal experimental design when you have a background model is the Fisher information matrix of a properly defined single observational unit. And as Valery showed yesterday, once you have this individual information matrix, you are essentially done because everything else becomes relatively simple. There are algorithms which are developed 40 years ago, some of them are developed 30 years ago, but they are very well established. And so the key is really the individual Fisher information matrix. In our area, the individual information matrix corresponds to a single patient on which we, on whom we have the observations, and it may be one or many. So we have multiple measurements per each patient. The calculation of individual information matrix. What we established over the last few years that when we make the same assumptions, the output of all 5 tools is identical. So which is nice. So there were a number of glitches. I personally did a few, but it was really helpful to have this option to compare with other tools because you know where to go. And Franz will talk much more later today about the comparison. Of course, there are differences, and I won't talk about differences, but there are differences in terms of implemented algorithm, how you select sampling sequences, which library you include, what types of approximation of the information matrix people use. So there are differences, but I believe that the core of all these 5 tools is very much the same, which I believe is a good thing. And you will hear more from Franz later today on this subject. Now, you have already heard some talks about pharmacokinetics and pharmacodynamics. It's just a quick refresher. Many people in the audience know this very well, much better than I do, but some people may not know this. And it's again, what is pharmacokinetics? It's pretty much how drug propagates in patient's body, and it's about the relationship between the dose of the drug and the concentration of the drug in the body. The pharmacokinetic studies are performed at different phases of drug development, very early in healthy volunteers, and then in real patients up to phase 3 and sometimes phase 4. The models which are used in PK, very often these are compartmental models which are described by system of ordinary differential equations. There are also non-compartmental models where you don't want to make any assumption about the background model, and what you try to measure is things like area under the curve, some sort of exposure, time to maximal concentration, and the value of the maximal concentration. But today we will talk about compartmental models mostly. And one of the most popular examples of PK model, you can find it in many papers on optimal experimental design in classic optimal design literature. This is example of one compartment model with first order absorption and linear elimination. It's a system of two differential equations, and sometimes pharmacokineticists like some block presentation of what's going on, and this is kind of a block diagram. You give a dose, this is your depot compartment, often called. This is the compartment 1 or central. There is absorption going on into your central compartment. There is elimination, and there is some volume involved. And Doug Bates at his talk on the first day used this model, even though I think Doug called this a two-compartment model. And again, I don't know very well all the nomenclature in PK, but I think the PK modelers call it one compartment model, even though there are obviously two equations here. So this is about PK. So PK is very much what your body does to the drug. So the drug gets into the body and something happens, absorption processes, elimination processes, and the concentration changes. Pharmacodynamics, on the other hand, is what drug does to the body. So it's how the clinical endpoint changes in time. So it's very often about the relationship between concentration of the drug and the effect it has. For example, you can look at the drop in blood pressure for patients who have high blood pressure. You may look at the reduction in the number of some bad cells, or you may look at the shrinkage of solid tumor. So these would be examples of PD endpoints. One of the most popular pharmacodynamic model is Emax, or sigmoidal shaped curve, which is nothing else but multi-parameter logistic model, which is again a very popular object in many classic papers in mainstream optimal experimental design. Now a few words about design of population studies. What we are trying to select or optimize, or what we control. Again, there may be in principle other control variables. What I will talk today about is where our main control variable is time. So we have to take measurements in time, and we have to decide when to take blood samples or samples from some other compartment maybe. We have to decide how many samples to take, whether it has to be 3 or 5 or 10, or depending on our resources, and whether we need to spend all our resources. If we can take 10 samples, should we take? Maybe 5 or 7 will be enough. And finally, we have to decide on the number of patients enrolled. So this question, I won't talk too much about the number of patients enrolled, because in terms of optimal design, I will talk mostly about the continuous optimal design, where everything depends on relative proportions or weights. But the number of patients will be critical when we try to compare the results of analytical formula and or approximations with some Monte Carlo simulation. And then the number of patients become really critical, how you organize your simulations. So what we call by optimal. Optimal with respect to precision of parameter estimates, because we will be working with parametric model, and that's why we need to introduce first of all the model, and then if we talk about the precision of parameter estimates, most likely it will be the properties of the covariance metrics of parameter estimates. And our goal is to find the most informative sampling times. So we want to minimize the variance in some sense, which is equivalent, as you all know, to maximizing the information. So the predictor in a typical model here is a vector. It's a vector of sampling times, say k. You have k measurements on each subject, and you measure k responses for each subject. As I already said, and as you all know, the key is derivation of the information matrix which corresponds to this k-dimensional sequence of sampling times. If we know how to calculate this information matrix, we are almost done. Unfortunately, I don't have this animation slide which Valery had yesterday with some crunching things going on. I cannot show it to you, but I'll just remind you that once you know how to calculate this information matrix, for individual patient, the next steps are really straightforward, because it's natural to assume that observation on different patients are independent. You sum up individual information matrices. You know that under certain regularity conditions, the variance of good estimators is inversely proportional to the information matrix M. We introduce the normalized information matrix, normalize it by the number of observations, and work not with these numbers N, but we work with relative weights, because the numerical procedures are really well developed for continuous optimization. And we work in terms of normalized information matrix or in terms of normalized variance-covariance matrix. Then we have to be able to compare different designs. For this, we need to introduce the criterion of optimality, which depends on the information, on the variance matrix in this case. And we do optimization with respect to weights, which have to be non-negative and sum up to 1. And we have to define what admissible sampling sequences are. So we have to define our design region. Once we do this, we're in a good shape and we can run the algorithms. Today, I will talk about d-optimal designs when we minimize the determinant. It's a nonlinear model, so again, I will be talking about locally optimal designs, and there are ways how to tackle it. With a locally optimal design, you need to run a lot of sensitivity analysis, but I'll stress that what we try to do here is not just to find optimal design for a particular setting. We also want to compare our optimal designs with other alternative designs, because in practice, some of these optimal designs is really hard to achieve. And again, Valery mentioned this yesterday about benchmarking. If we can find that the alternative design is, say, 90% efficient or 95%, we may be in a good shape. But if we see that the alternative design is 40 or 50% efficient, we need to do something with that. The main tool for the algorithms is the equivalence theorem, which goes back to Kiefer and Wolfowitz. And the algorithm which we use in our tool, and I know many other developers use, is Fedorov-Wynn algorithm. And we have both of the developers of this classic algorithm here in the audience, which is very nice. So, please correct me if I'm wrong. The first papers talked only about forward step when you add points to the new design to improve. You have also to delete bad points from the design, and I believe one of the first papers, or maybe the first, was a paper by Atwood in the first volume of Annals of Statistics, where he suggested to remove bad points from the optimal design. Valery said yesterday that he doesn't have pictures of the ellipsoids, and we had some discussions about different criteria of optimality, whether D is good or not, and how it's related to others. So because of this, I decided to bring on some picture of the ellipsoid here. And this picture actually illustrates, and I'm sure the absolute majority here know, the relations between different optimality criteria. And in fact, in two dimensions, it's really easy to illustrate how all of this, not all, but at least 3 criteria are related. You remember there is a relationship between the values of criteria D, A, which is linear criterion that trace, and E, which is the maximum eigenvalue. And this is the geometric illustration, just to refresh your memories. So this is the ellipsoid of concentration built with the variance-covariance matrix D. What is the D criterion? D criterion is the determinant. It's simply the product of the principal axis of ellipsoid squared. This is the main, this is the first principal axis, the largest, this is the smallest. You take the product of the principal axis and you calculate the determinant. And by the way, the volume of ellipsoid, or area in this case, is simply square root of this product, lambda 1 and lambda 2. The E criterion is the maximum, the length of the principal half-axis squared. This is the guy. And A criterion, which is simply traced here, is sum of the eigenvalues, same as the sum of 2 diagonal elements. And again, what you do, you surround the ellipsoid with this rectangular, will be square where the principal axes are equal. You take the diagonal of the rectangular and you square it. And you see from this picture, hopefully, that all these different criteria are related to the size of the confidence ellipsoid in one way or another. And all of them are closely related. And we stick with D criterion. And again, because equivalence theorem works for other criteria, we can do other criteria too. We have not implemented other criteria in our tool. I know that in other tools there are some variations, and maybe the developers can mention this. All right. So if we know the information matrix, how to calculate it, we know how to run standard algorithms, we know how to solve the problem. Let's now talk about what kind of models we consider. And on this slide, I have the standard mixed effect models, which is typical for many, many applications in PK and PD analysis. First of all, we have the response parameters of the model, and these are rate constants like absorption rate, elimination rate, volume, etc. Then we make an assumption that parameters of individual patients are random, so they are sampled from the population. The typical assumption is that the parameters are either normal or beta log normal, because again, from the background of the problem, all these parameters have to be positive. Then we form the measurement model, and we have both the additive component of measurement error, and we have the multiplicative component of measurement error. And those who are familiar with the tool called non-mem, which is standard for many pharmacokineticists and pharmacodynamicists, would immediately recognize that this is a standard model from non-mems, which is very well familiar to, at least in drug companies, everyone is using it. The combined vector of parameters. We are interested for the population model in the estimation of means, gamma, which I denote gamma 0, the population variance covariance matrix omega, and we are interested in the estimation of these residual terms sigmas. How the response function eta looks like for one compartment model, which we talked about a few slides earlier. This is the sum or the difference of the exponential function, and again, there may be different parameterization. They may be parameterization through rates like elimination rates, or it may be a parameterization through clearances. I think Doug used the parameterization through clearances. Though, and please correct me, this is the question to people with a good pharmacological background. From what I heard from our PK/PD modelers, they don't combine elimination rate and clearance together.
It can be. There's three ways you parameterize the model. All of them work, but the key here from a design perspective is that when you have clearance, elimination rate constant, absorption rate constant, and you have random effects on those, then the designs aren't invariant to reparameterization now. So it changes the design space, changes the location, and actually the search for the design is very nasty if you use clearance and elimination rate constant as your primary parameters. So it really makes it much harder. Clearance, volume, and Ka is probably the easiest parameterization. So that one you got there is okay.
Are you in the log normal? Are you
Yeah,
using log clearance?
Yes. Yep.
But aren't you just taking a difference then? Isn't clearance something like the
It's a ratio. The clearance would be, or the product of K times V. But you find that if you look at it in the normal and log normal, you find the information matrix is quite different. The surface of the determinant is quite different under those two parameterizations.
And by the way, I noticed that some PK/PD modelers are very picky with the notations, like maybe statisticians are. When we work with linear model, we like notation X for the design metrics, theta or beta for parameters. Once I used capital K for the rate here, and one of the PK/PD modelers said, no, you have to use the small k. That's how my professor taught me. But, you know, everyone has his or her own preference.
Well, yeah, one could not like mu for things that sum to n too, couldn't one?
Yeah.
Yes.
All right. So,
before you continue,
yes.
I like all these discussions about what to include, what not to include. And I remember your remark yesterday about that model should be somehow consistent with experimental or with understanding what is going on. And whenever I read these papers about PK design or PK modeling, you always have this additive noise. And potentially your concentration will be in blood negative. And very much negative. So why not to introduce some reasonable parameterization of this error to avoid this?
But negative concentrations are fine.
I'm not sure.
This is actually an important concept. The idea here is that you don't see a concentration, you assay it. And that assay has got another regression model attached to it. And it doesn't have a zero intercept for that regression model. So the assay itself is going to predict a negative concentration from time to time from what it sees in the blood. So the actual concentrations, of course, are never negative in the blood, but you might report a negative concentration from the assay because you're a non-zero intercept.
You can, but it's more natural to introduce some trivial transform.
And therefore the model actually is predicting what the assay is seeing. And therefore the assay will see a negative, despite the fact that it's not truly negative. But the observed concentration can be negative.
Yes.
The predicted concentration can be negative, but the true concentration can't be, and neither can the model prediction in the absence of error also shouldn't be negative. So it actually fits in.
Yeah, it's correct. You know that observed could be negative, but real.
Oh, yes. But we
But
only
let
observe.
us introduce this positiveness in model from the very beginning.
Well, the assay people do that because they just censor anything which is embarrassing. They take it away from us. Which causes huge numerical issues.
Let us
Anyway.
continue for a while, and we can continue this
It should be
discussion.
reflected in your information matrix, because from the very beginning, your model for errors is very approximate, especially for low. And now you start to fight for some kind of minuscule corrections.
Well, as we'll see, there are so many levels of approximation here, so it's one of the components, I would say. There are a couple of things which everyone uses, at least the developers of the tools. And there are some classic and some simple results from statistics or from calculus. First of all, there is a standard result in multivariate statistics about the information matrix of a random vector which has a Gaussian distribution with certain mean function and certain variance covariance matrix. You can find this information matrix, and this formula, this general formula, you can find it in classic text, takes care actually of the situation when variance depends on unknown parameters. And this is the case in many of our applications because we have the proportional component on variance. Keep in mind though that this is true. This is an exact formula, but only for Gaussian y's. Yes?
I hate to bring up another meta, but is it really the expected value of y given x is eta? Because you have the additive noise and you have the multiplicative noise.
Yes.
And if I'll agree that it's the expected value with respect to the additive noise, but
And with multiplicative, then the next step is the first order approximation, of course. Once you have the first order approximation, you know of all these formulas in linear mixed effect. With nonlinear, you just do first order Taylor expansion. And that's what we all use. I'm not saying that this approximation is always good. Sometimes it's pretty bad, and I'll show you the examples.
But first formula is accurate. It's a precise formula for any situation. In frame, which is in frame. Are you talking about formula in frame or which is below this frame?
This formula is true, but then, you know, because we have individual parameters when we have random parameters.
It doesn't matter, it's still win.
Oh, yes, the first formula is always right,
one
but
is still
nonlinear
weird.
mixed effect model doesn't follow the first formula. And we try to make them follow that.
Excuse me, the first formula is not right. It should be conditional on x and theta.
Yeah.
And everybody's lazy about
yes.
it. Everybody's lazy about
Thank
that. But if you have a random parameter, you have to be very careful.
Thank you,
Yeah,
Ken.
it's expectation with
The same
respect to
comment I
errors.
made with the lyrics.
Yes.
That's what we call theta.
In this case, theta is fixed parameter.
Yes, here theta
In this
is
case,
clear.
Which one?
fixed
Yes.
in a frame formula. Theta is
Yes,
fixed
theta
parameter.
actually, theta here.
You're talking about mixed model.
Excuse me, is it fixed any more than x is fixed?
X is not fixed, but you can treat X as fixed also.
And you can treat, is it not conditional on x and theta? Depends which world you live in, really.
X is fixed and theta is fixed. The only what varies is Y capital in this formula.
The first formula is just for non-linear regression with given.
It's a standard formula under certain value of parameter theta. So I will take this theta under the expectation sign. All right? So,
for random
the
effect, it's population. This is what they call hyperparameter.
I think it's
There are
time
some
to let the
buzzwords
speaker
about
Okay.
continue.
So the first formula, again, I hope we agree, is true for Gaussian only. This is the first order approximation. And the formula is familiar, again, from many applications. And we have next to define what our candidate sequences are. And for this, I give an example how we implement it in our tool, which is called PK-STEM. And this is where the abbreviation is coming from. We allow selection of sampling sequences in two ways. First of all, the user may specify a sequence of candidate sampling times, and then number of sampling times per each patient, which has to be bounded between certain numbers, again, which the user may enter. And we also introduce the lag between sampling times. So it doesn't make sense to us to sample too close to each other. And this lag may be equal to 0, but you may force to this constraint. The second option, a user can pre-specify arbitrary set of candidate sequences in a file, whichever you wish, and then find the optimal design from these sequences. Whether it will be at the end one sequence or many with different weights, it's up to the algorithm to decide. So this is a specific type of constraint on design region, what Basha asked yesterday, for example. And again, some tools have algorithms which allow the continuous change of time, because time is continuous. We discussed it with our modelers, and we agreed that it really, again, you can do this, but you make your life much more difficult. What we actually face a discrete optimization problem. We first calculate all candidate information matrices and then work in the space of individual information matrices. So the optimization step is really very, very simple. And in practice, if I don't allow to sample at time 1 hour, 33 minutes and 55 seconds, who cares? If I say you can sample every 10 or every 15 minutes and provide the sequence in some way, again, we discussed it with our modelers and they were quite happy with this type of selection. This is how the screen looks like. I won't spend any time on this. I just mentioned that there is a library of models. Similar things are in other tools. You select your parameters, you select population covariance matrix, you specify the measurement error model, the dosing regimen, what kind of sequences you have, and plus at the end you have an option of efficiency analysis, and you can compare the calculated optimal design with any design which a user wants to specify. Plus you have an option of sampling windows, and Steve will talk today about sampling windows. It probably will be a little bit different from what we do, but it's a similar way. You test the robustness of design. You produce some sampling times, but in practice the nurse in the hospital cannot stick the needle exactly at 30 minutes after administering the dose. What happens if there is some shift, plus minus a few minutes? Second, so an important thing, I just want to show that we can address more complex setting in general. We may introduce cost-based design. Franz has already talked about cost-based design in her talk. So instead of normalizing by the total number of patients, you normalize by the total cost, and you get a different type of normalization of the information matrix. The thing is that numerically there is no problem once you have this, once you have this cost function defined. If you know how to define the costs, it will be the same algorithms. And there was a paper, many of you know, especially in the mainstream design literature, by Gustav Elfing on optimal design and geometric construction. He actually introduced this concept of cost-based design. So that goes back to the 50s, to Elfing's paper. There is a more general setting, and you can find it in the survey paper by Dennis Cook and Valery a while ago. What we have in our tool, we have costs which may be proportional to the number of samples, or you may enter any cost function which the user may define. I have to admit that even though we talked about costs for a number of years with our modelers, I cannot say that this idea of cost-based design have flied too far, because they have not really used it. And one of the reasons is it's very difficult to introduce a reasonable practical cost function. And again, Franz had examples in her talk, and it was just mostly to illustrate that you can do it. But once again, if you know how to define cost, you can run standard algorithm. We can address more complex models. For example, nonlinear kinetics, when there is no analytical solution to the system of differential equation, not only our tool, but other tools too. For example, this is an example of Michaelis-Menten model. And there are a number of papers in mainstream design literature on Michaelis-Menten. I believe Jesus Lopez Hidalgo and I think Wenki also published on this. Even though you took this Michaelis-Menten as a PD endpoint in a sense. Here we have this term in the system of differential equation, this nonlinearity. For this we have to use the solver, numerical solver to address. We can address problems with both PK and PD models. So this is a PK model, again, one compartment model, and the output from PK model, the concentration, is the input into PD model. This is an Emax. And we can measure PK and PD compartments in general at different times. So there are a number of options how to do this. Another example which we did just a few months ago and even continued doing during this week This was an example proposed by France for a specific study, which I think France was involved with her colleagues. Look here, so this model looks not as a very easy one. So we have a PK component, and this is still the one compartment model with first order absorption. We have a PD model, and this is for the drug to treat chronic hepatitis C. There are a number of PK parameters here. There are a number of PD parameters, and I just give you the structure of the model. So the PK response enter the PD equation, and this is the system of nonlinear differential equations. And all software tools can handle this model in terms of crunching the response and then doing our standard things. I'll skip the details of how we implemented. What I want to say that over the last 2 years, a little bit more, thank you, the development of our tool was the collaboration of my older, long-time colleague from my Moscow home institute, Alexander Aliyev, and I think that he personally did a great job in doing really nice programming thing. I was doing this myself for the first 5 years, and all programming work is now done by Alexander, who is a better programmer than I am, and I really enjoy the collaboration. So for user-defined option, you can actually tackle essentially arbitrary, within certain limits of course, system of ordinary differential equation. You can introduce closed form solutions in this, how you define the system. You can theoretically tackle arbitrary number of compartments, but of course I won't go too high. Some people tackle 10, 12 compartment models. I won't touch this because I won't guarantee the quality of calculations for that type of models when you have tons of the parameters. I'll skip this. Don't have too much time, but all right. About the comparison of Fisher information metrics. 2 years ago, we did our first test, and we compared the output for simple one compartment model for different models. It was a simple one compartment model which I presented with 3 parameters, with the diagonal variance covariance matrix of random effects, with proportional component of variance, of measurement error. The information matrix has a block diagonal structure, and this is the typical notation which goes back to the paper by Sylvie Ritou and Franz Montre. There is a block which takes care of derivatives with respect to response parameters. This is the block mixed derivatives. B is the block of derivatives with respect to variances. So that's what we all use. What we compared? We compared the analytical information matrix, how it's calculated by different tools, and found out at the end that the results were identical for all. And what we did, by the way, we compared it just for one particular sequence of sampling time, 8 times, but the numbers came from an earlier studies. What we observed, and then we compared this analytical result with empirical variance covariance matrix, just Monte Carlo simulation, and then running estimation independently in non-mem and in Monolix, the tool which developed in Paris. And what we found out, if you exclude this non-diagonal block C, and if you exclude the second term in block A, the trace term, the results of the analytical calculation and the empirical variance covariance matrix were essentially the same. Once we included block C for this example, there was a substantial discrepancy with respect to some parameters, which is a strange fact, and I still don't understand completely why. One of the reasons why is, for this example, we used log normal distribution of parameters, and we used first order approximation. So for first order approximation, you approximate the exponent as 1 plus xi. So the approximate mean will be 1, the approximate variance will be v, but the exact moment for log normals is here and here. And if variance is substantial, then the first order approximation gives you 1 for the mean. The true one is 35% more. The variance is 2.5%, twice 2.5, factor 2.5. So we approximate one thing with completely wrong. Second thing, you can of course try second order approximation for mean and variance. The thing is, it numerically may be rather tedious because we calculate all derivatives numerically. For the variance, we need second derivatives of response function. Then we will, second order approximation, we will need fourth derivatives, which I personally won't go for. What I think is a better approach is just to calculate mean and variance via Monte Carlo. Just generate n samples from this particular distribution, since we know parameters. Calculate empirical mean and variance, and it will be numerically really straightforward. And again, if we trust normal approximation, again, the general formula for the information matrix works for normal approximation only. This would be close in my mind to first order conditional expectation approach, which is kind of standard for many other tools. We don't have it, but other tools do. And this goes back to paper by Lindstrom at Bayes. There are some other work which has been done in this area, and I think Tobias will talk later today and maybe expand on the results which he presented last year at MODA. So we will see, and Joachim will have a talk also talking about different types of approximation. To summarize, we all know that for nonlinear models there are many difficult things to address. There are different measures of nonlinearity for nonlinear models. There are all these curvature measures like intrinsic curvature and parameter effects curvature. There are a number of papers which go back and books on this subject. There were simulation studies performed for PK/PD models, and one paper which I think is very interesting and reasonable to read for many is 10 years ago by Merlet and Todd, where they did simulation studies comparing the first order approximation with Monte Carlo. What they observed that the criteria values may be substantially affected by linearization. Of course, we are using not the right object, but at the end, designs and relative efficiency of these designs are often not very much affected. I think that the way forward would be to use some sort of Monte Carlo here, especially with all this numerical calculation of derivatives. I think it's about the same in terms of computer burden. And again, our comparison during the last 2 years showed that linearization is indeed very, very crude, but it performed reasonably well under certain assumptions. And again, I still don't have an explanation why. Maybe Franz or other developers can give some hints. Final slide, optimal design for PK/PD models. I was working on some survey text recently and carefully read paper by Catherine Challoner and Verdinelli on Bayesian experimental design. Many of you know this paper, survey paper 15 years ago. And this is the quote from the paper. There is a rich related literature, mostly non-Bayesian, on design for complex PK and biological models. With a few exceptions, this important work is not in the mainstream statistics literature. So I hope that what we are doing in PODE is kind of contributing, moving this literature and these models and this work into the mainstream, and hopefully if more and more people from mainstream design come to this area, we all will benefit from it. And so thank you very much.
Very brief discussion is allowed, as we had some already.
That's not that brief. Ah, okay.
So just on the computation, when you have these complicated models, you have a solver, and the solver produces what the engineers call the sensitivities, the Jacobians, automatically as the solver runs along. Is that right? Because that's what happens typically in like climate modeling using conjoint analysis or something. So at the same time as it solves, it also produces the Jacobians, yes? Or is it a separate step?
I did not go into the details of the solver in MATLAB. I don't know if other developers, Joachim or Kay, can.
I hope that is a separate step.
Because we are using like a standard solver, this OD, whatever. I mentioned this type of model at another presentation, and Jim Ramsey, who wrote a book on functional data analysis with Bernard Silverman, mentioned that some of this type of nonlinear differential equations may create some problem for the solution. So this is a separate issue. I just brought this slide here to show that at least we try to address relatively complicated dynamical system in our.
Kind of very quickly, the reason I mention it is there's a very large literature in computational sensitivities inside the engineering literature using various different methods. So that would be another kind of area that people from that community could come to some of the.
Okay, yeah, thank you.
Yes, there were other questions. Steve, please.
This is I guess slightly tangential question about using de-optimality, which all of the packages use. But since there's inherent nonlinearity in the system and parameter curvature and intrinsic curvature, then why don't we use Barbara's Q-optimality?
It's not right.
Well, you wrote about it, but I've never seen anybody publish on Q-optimality, at least in our literature
the
ever.
calculations become very tough for the.
Sorry for a dumb question. Can you remind what Q-optimality is?
It's well, I just called it Q for curvature. But that includes.
Quadratic approximation.
One thing which I want to kind of comment. We had many discussions with the PK/PD community in JSK while we were there.
The point is that this includes the measures of curvature.
Okay. It would be nice. What the practitioners accept, they say, yes, we understand that there are many layers of approximation. First of all, the model itself, not necessarily true. Then you use approximation of the Fisher information matrix. You may use approximation of sampling times when you do this sampling windows thing. So, and they said, we still try to validate your results using our tools, for example, using different types of clinical trial simulators. I still think I'm a mathematician by training. I don't like to use really a bad formula in the code when I know then when I approximate log normal with a big variance, it's actually bad. So it would be nice to have something better, but it's still an open field.
Anthony.
This software was developed at GSK.
Yes.
Does it die as you all leave GSK?
No, it's here. Well,
okay, are you going to be arrested?
Well, how we developed our tool, it was a standalone. It developed in MATLAB, and MATLAB allows to create a standalone. It allows to create an executable. You don't need MATLAB license. And I talked to the guys over there, and they actually told me, well, we never sold this software. You don't plan to sell it, so they did not see any problem of continuing developing it. So, but
it's important.
Yeah. Okay, last question.
There's more a comment about the geometrical characterization, just a bit of history. It was David Silvey who proposed in the discussion of Henry Wynn's and Patrick Leacock's paper that the smallest ellipsoids containing the design space would define de-optimality. But it was Robin Simpson who went on to prove that conjecture in his contribution in a later paper. And that seems to have got lost, judging by a discussion I had last night, that's kind of got lost in history.
Yeah, it would be good to know the reference if you could provide.
Getting a bit lost in history ourselves.
I think time for coffee now. So thank you very much for discussion and